An object is suspended from a vertical spring as shown in figure 3.1, the textbook example of an object undergoing simple harmonic motion. Mass attached to a spring. Another example is motion of a simple pendulum. Another example is motion of a damping system or earthquake proof damping system. Another example was motion of an electron when alternating current is supplied or flows through the conductor. So there are plenty of cases which exhibit simple harmonic motion. Here we have this one. So there are plenty of cases, but this is the most fundamental one probably. So what do we see here? What we have is, you can see we have a graph of energy with respect to the displacement from the mean position, and the mean position at this case is 0 when the displacement is 0. So this is the mean position, x equals to 0. So why do we have such a graph? And let me tell you, this is a standard graph. This is a textbook graph of all the energies of an object undergoing simple harmonic motion. Kinetic energy, potential energy, total energy. But let us break it down into 3 segments. If we talk about the first one, there's a horizontal line over here. What energy would this one be? It is an energy that does not change throughout the motion. What energy could it be? Could it be potential energy? Could it be kinetic energy? Or should it be the total energy, the one that does not change? That should be total energy. Agreed? Okay, then we have a certain energy which is represented by this curve, as you can see over here. A certain energy which is represented by this curve, and this is an energy which is maximum at the mean position. This energy is maximum at the mean position. This one is mean position, the central one. This one is extreme position. This is also extreme position. Now what is the energy that is maximum at the mean position? Which one? Kinetic energy. Excellent. So it means, even by method of elimination, we would know that the last energy has to be none other than potential energy. Yes. So we don't know what the question is, but commenting on the graph here, if we talk about the total energy, can we read from the axis and quantitatively answer what is the total energy? I think 6.4. Yeah, I think this one line is 6.5. What do you say? So this one 6.4. So the total energy that we have is 6.4 millijoules. Do not forget to read the axis for the exponents for the prefixes. So this is 6.4 millijoules. What could the maximum kinetic energy be? Any idea? And maximum potential? Because the maximum kinetic or the maximum potential can never exceed the total energy. The only difference is maximum kinetic would be at the mean position, but the maximum potential or the potential would be maximum at the extreme positions. So we did not even read the graph, read the questions. And if the object is undergoing simple harmonic motion, there are plenty of expressions that we can use. A equals to minus omega square into x. One of them is v equals to x naught omega, or you can write it as v equals to a omega. Amplitude can be represented either by x naught or a. Doesn't make a difference. We should be aware of both the notations. Omega equals to 2 pi over t. or you can say omega equals to 2 pi f. So any of these expressions can be used for this, uh, for finding any of the thing. If we talk about the energies, the maximum kinetic energy, which is equal to maximum potential energy, which is equal to the total energy. For that one, the expression is 1 over 2 m omega square a square or x naught square, means the amplitude. You can either write by x naught or capital A, it doesn't make any difference. So these are some of the formula which could be used for the following parts. Okay, now let us see what do we have. State the energy that is represented by each of the line PQR. We solved this one already. P is total energy, Q is potential, R is kinetic. Total energy, potential energy, R is kinetic energy. Let me confirm. Yeah, R is what do we call that? Kinetic energy, because it is maximum at the mean position. The object has a mass of 130 grams. Determine the period of the oscillations. Okay, so mass is given 0.130. This is a mass in kilograms, and we are required to determine the period of the oscillations. Okay, so T equals to 2 pi over omega. Easy as you like, because omega equals to 2 pi over T. 2 pi is just a constant. The only problem is at this stage we don't have the value of the omega, and if we need to find omega, omega would be equal to 2 pi over T. But the problem is you don't have T. In order to find T you need omega. In order to find omega you need T. So you are stuck in a loop, endless loop. So we need to get out of this one and try to come up with an expression to find omega other than the one that contains capital T. Do we have such an expression? Yes, we do. Since we are provided with the energy graph, I can use the expression the total energy, which equals to the maximum kinetic energy, is equal to 1 over 2 m omega square x naught square. What was the maximum energy? 6.4 into 10 raised power minus 3, 6.4 millijoules. You see, we wrote it down even before solving the questions. That equals to 1 over 2. Mass is 0.130. So omega would be written as it is. I'll just write omega as it is. X naught, or should I say capital A? Okay, totally your choice. Please keep yourself open to any kind of notations, because they may not necessarily be representing a certain quantity with a specific symbol. So we should open up ourselves for any kind of notation. X naught or A represents amplitude. What is the amplitude? The maximum displacement from the mean position. So is it not this one? What do you say? Isn't it this one? So how many blocks do we have? 10 blocks represent 0.4, 1 block represents 0.04. So 2.24, 28, 32, 36. Need to zoom it in. Okay. So 1.24, 1.26, sorry, 28, 1.32, 1.36, 1.4, 1.44, 1.48, 1.52. So 1.48 and 1.52. And this one is exactly in the middle of these two. So how much would it be? 1.50. Absolutely. I mean, that was, to be honest, that was easy. All we could have done, that this one was exactly in the middle of, yeah, this one was exactly in the middle of 1.4 and 1.6. That should have been an easier option. We know exactly in the middle of 1.2 and 1.6 is 1.4. So this is 1.4, and one exactly in the middle of 1.4 and 1.6 should have been 1.5.